Hello everyone, it's Jimmy from Jimmy Math Tutoring. Today we're going to look at, I'm going to do a sample problem, of a calculus, pure type calculus. It's like an integration type problem. But it's to answer a simple question, which was, the question is, what is the volume of a cone? A cone, has the shape like this, and it has, a circular, bottom, and how. So you may remember, what the volume of a cone is, from like geometry, and I think probably, if I remember correctly, it was, it was 1/3 and pi r squared h. I think that's what it was, if my memory serves me correctly. But what if you forgot, or you wanted to make sure, And so this is not really a problem per se, but we're going to use calculus to derive the volume of a cone, And this is a legitimate problem. I mean, because you'll be using, methods to calculate volumes, using integral calculus. So we're proving, that the volume of the cone is that, and it has radius r and height h. So that's what the cone looks like. And so how are we going to do it? Well, we have to set up our coordinate system. That's the key to doing this. So we might as well just say, here's our coordinate system. We're going to set it at 0. The origin is going to be the red point, and it's going to go up and out. The x and y. Here's the x-axis. Here's the y-axis. And what we really want to do is we want to set up an integral. So we need to set up the integral. And are we going to use how are we going to do it? Are we going to use shells or what? So that's the question. I think the method of shells could work here. But what would the other method be? Well, it could be washers. You could do washers. Washers would be like going around using this as the thing and integrating along the y-axis. And shells would be integrating along the x-axis and going up. So it's just your choice which one of those two that you want to do. Sometimes it could be easier one way than the other. In this case, I don't think it really matters. I think either way can be done. But I always like to get my equations in the form of y equals some function of x. And I think I'm going to do it this way. I'm going to use the method of shells. Because it's so what is the equation of this line? The line that I'm interested in, is this line right here, this blue line, that is set up on my rectangular coordinate system. Well, that goes through the point R0 and 0h up there. Up here. See, so we've got 2 points on that blue line, so we should be able to calculate the slope, which is y1 minus y0, which is h minus 0 over 0 minus r. So the slope is equal to minus h over r. That's pretty simple, there. So now, we use the, we need to write the equation of this line, of this blue line, so I'm going to just put it in a blue box here for you, and let's see what it comes out to be. Well, it's y minus y1, which y1 could be, let's take this point. We have to pick a point on the curve. So y minus y1, so that's y minus 0 equals m, which is minus h over r, times x minus x, so r. Y minus y1 equals m times x minus x1, x1. So that's the equation. It's y equals to h over r times r minus x. If you want to do it like that, that's fine. That's the equation of the blue line. And it's important. So we set it up, that way. And so how do we use it? You see, that's the question. Well, now we are going to set up the integral. That's where, calculus comes into play now. We're going to set up the integral because, we now know, what we need to know. We know this height in terms of y. That's our y. And we know that, we're going integrating along the x-axis from 0 to r. So, So what are the limits of integration going to be? Well, let's answer that question. Limits of integration, well, it's going to go from x equals 0 to x equals r, because that's the radius of the, of the bottom circle there. See, 0 to r, we're going to go, integrate it along that, place. And but what is the shell method? Well, the shell method. See, here's the key. The shell method. What it does is it takes a little thickness, of this, thing, and it rotates around. You see, it rotates and creates a little miniature, shell inside of there. See, if I did my drawing right, it would just be a small little circle in there, and that is a well, now see, that's a good question. Is can you use the shell method, to do this? And I don't know if that's In fact, I think washers may be the way to go with this, because see, with the shell, no, it's okay. It's okay, I think. Yeah, it's okay. We can do it. Anyway, so that's just a little thickness. So let's blow up what that shell looks like, just so you can see what I was thinking about there. It's been a while since I've done a shell problem, but here is what the shell looks like. You see, blown up. See, it looks, like that, but you see, it has, a thickness, a small thickness. That's why they call it a shell, because it's not really, it's just it's a very thin, cylinder, it's not, it's not a solid, it just has a thickness, a very small thickness, and everything else is hollow, you see. So, that's why I'm saying, we add up all of these shells as we, go along, and we will fill up, we'll fill up this complete, cylinder, cone. We'll fill up the whole solid three-dimensional cone. So, we've got our limits of integration, but what are we going to integrate? Well, what is the volume of the shell? See, that's the question. The volume, because the integral is going to be equal to, the volume is going to be equal. Let's just go over here and write that. Let's try to set up our integral over here so that we can go back and refer. So the volume of the cone is going to be equal to the integral from x equals 0 to x equals 2r of dv. See? Every incremental volume, you see? And dv is equal to this orange shell right here. See? That's your dv right here. And as you do all of those shells, that's it. So what is that volume of that, thickness of the shell? You see? Well, that's the question. We have to get that formula. And the thickness of that orange thickness, we can call that dx because we're integrating along the x-axis. So that's not a problem. So dv is equal to, well, the way that I think of it is, I say, here's the way I think of it. I think cut this shell, at some point, like right here. Just cut it, with a pair of scissors and unroll it, and you'll end up with, let's see what but first here's the 0, here's the point x. So we're out to radius x at some point, x. You see, because we're going from x equals 0 to 3, but arbitrarily that's just x. That's the radius, Now what is the height in terms of x? What is this height in terms of x? That's a good question. Well, that's where this comes into play, you see? That's what it is right there. So let's plug it in over there. It's h over r times r minus x. And then so we should be able to write that incremental volume of that shell in terms of x now. And so that's where I say cut it. It is cut it lengthwise and then unroll it, and you'll just get something that is like a rectangular slab, like this. You just get a rectangular slab, and the thickness will be dx, and the other dimensions will be these two things. You see? Well, actually, it won't be x, it'll be 2 pi x, because that's the circumference of the circle. So the length of it will be 2 pi x, and the height will not change. It will be just h over r times r minus x. So that's the only thing, that's different. That if you cut it and unroll it, you get this slab, and it has rectangular dimensions, so we can just multiply them together, and we get dv equals to 2 pi x times h over r times r minus x dx. See? There we go. We've got something we're working with now. And so now let's plug that back in up there to our formula. You see, we're going to plug that in and see where it takes us. So integral 0 to r of dv, which is h over r times 2 pi times x times r minus x dx. It does seem a little complicated, but hopefully it'll work itself out, So we pull the constants out, 2 pi h over r. Go to 0 to r of, now here where we can just say rx minus x squared. And so, now it's an integral, and we can, integrate that. So we get rx squared over 2 minus x cubed over 3. And that is 2 pi h over r, going from r to 0. So, now I've got 2 pi h over r and then plug in R, and we get